All right. Guess what time it is? It's Leetcode time. Okay, so let's get started. Let's move forward. So make myself a little bit smaller there, and I am obviously doing backtracking right now. So let's randomize it and pick one and just try to keep practicing. And the most important thing to be doing right now is we do the problem, but we try to identify those points at which there's a stumbling. Because if there's stumbling, then that means that is an opportunity for us to learn, or it means that there's something in, and we need to identify it, right? Either it's an off by one, or a concept that I don't quite have solidified, or it's something else, right? There's something that is causing me to trip up. So we need to identify that and try to fill those stuff in. Anyways, let's get started. And okay, next medium looks like it's this one. Okay, circular permutations in binary representation. Okay, so given two integers in and start. Okay, so we're given two integers in and start. Your task is to return any permutation p of 1 to, so this n is the exponent given to us, okay, such that p of the 0th is equal to start, okay, and p of I, which where is I? I is each element in the array, okay, differ by 1 bit in their binary representation. Okay, so its neighbor, each neighbor differs from its previous one by only 1 bit. So for example, I would have whatever, like 4 is equal to hexadecimal 00. It's not like, oops, like this. There we go. Right? So this is the ones place, this is the twos place, and this is the 4 place, this is the 8th place. Okay? So now, can we do 5? Yes, we can, because 5 is going to be equal to hexadecimal 0101, kind of like that, right? And it differs by 1 thing. So 4 and 5 can be neighbors. Could we have done 4 and 6? Yes, we could have. Because, watch this, 6 is equal to hexadecimal 0110. And notice this bit right there is the only one that differs between 4 and 6. Could we have done 7? No, we can't, because that's going to be like this. 7 is going to be like that. Okay. So we could have done 4-5 or 4-6, or what's another one that we could have done? So let's change this one right here. So this is the 8th place, so 4, 8, 9, 10, 11, 12. So 12 we could have done. 12 is equal to hexadecimal 1100. Okay, so this is the bit that is changed. Okay. Now the second thing that we need to do is p of 0, the 0th index, And the last index must also differ by 1 bit in their representation. Okay, so I see why it's like circular. So, like for example, the first element could be 4, and the last element could be 12 because they differ by 1. Okay? But P of 0 needs to be start. Okay. All right. How are we going to do this one? Okay, so input. I'm just gonna look at the example. We have n equals to 2 and start equals to 3. Okay. So the output is 3, 2, 0, 1. The other thing that I'm thinking about is like, what's even the point? We're not trying to minimize something, right? So this isn't a minimization problem. We're not trying to maximize anything. The point of this problem is to return any permutation of P, any permutation P of 0 up to this thing, which this thing is n. So we're given n and we're given start. Okay. N is 2 and start is 3. So we have to start with 3, okay? And now 1 and 3 differ by 1 bit. That makes sense. 3 is going to have 1s in these two places here, and 1 is going to have a 1 in that place, so they differ by 1 bit, which is right there. Okay, so they wrap around. Okay, all the adjacent elements differ by 1 bit. And it has 0, 1, 2, 3. Okay, there we go. So it's just counting up. And it's a permutation of the 0, 1, 2, 3. And it stops at 2 raised to the power of n minus 1. So 2 raised to 2 is 4. Okay. Minus 1 is 3. So it stops at 3. Okay. So obviously I pressed on the backtracking problem set. I got this from the backtracking problem set. So that indicates that this is going to be a backtracking one. So backtracking is to fulfill every single instance, or not instance, but like explore every single option. Okay. Oh my. Okay. Interesting. Okay. So what am I going to do? So def backtrack, okay, something, and then obviously we're gonna need a base case. If, so we can calculate the last number is equal to 2 raised to the n, okay, minus 1. So if number is equal to last num, okay, what do we need to do in this case? We need to check if it's valid. So I'm just going to say check if valid. And what does valid mean? So if num is equal to we need some way of checking if it's 1 bit off of can't get internet. Okay. We need some way to check if it's 1 bit off. One of the things that I was thinking is a bitwise OR operation. Masking. Alright, so bitwise things are not kind of what I'm trying to go for right now. Like, okay. I actually am going to take this to Copilot because, and I'm going to ask it in a very specific way. Copilot, here. How can I get, or how can I determine if a number is only 1 bit off of another number? Do not give me the answer to the problem. Only tell me how to do the bit comparison. Nothing else. Okay. Awesome. I'm just going to copy and paste this. Okay. There we go. So, if is, so the reason that I just copy and pasted that is because I'm trying to learn backtracking right now, not bitwise operations. Okay, so maybe we can investigate what it's doing in there. But I'm trying to get the concept of backtracking and trying to understand how this is working right here. So num and last num. Okay, so if these two are 1 apart, then we have a valid string, or not string, but like permutation. So I obviously need something like permutation. So self.p is going to be equal to empty list. So I am going to append, so p dot append Or maybe we don't append it right here, actually. Return self.p. Okay. This might not work exactly right now. I might not even have this num. So let's go look at the different cases. So what do I want to do? I want to I think I need like a list or something. I'm thinking I need to add a number to it. I need to take away a number to it, right? That's kind of the way backtracking works is you add the number, you try adding this number in the next slot. Then you explore. Okay. So you move on to the next one. So it would be something like self dot p dot append and then num like this, but we would need to check if it's valid, right? And then we would do backtrack on num plus 1, okay? And then we would self dot p dot remove num, kind of like this. But first we need to check if num is valid. Okay, so how would we do that? Like if this is different, num, the number passed in, okay, and the future, or the last self dot p dot, or indexed at the last element, okay, if they are one apart, then it's a valid number and we can append it and explore for future options. If not, we don't explore that option. Okay. Okay. Self.p, so we return that list. And num is I need some way of guaranteeing that I always put all of the numbers in, right? So that's why I was thinking like maybe I need a list. Something like for I in range 0 to last num, but actually that would be plus 1, right? Because this is a -1 and this is non-inclusive. I would do counting dot append I, kind of just like 1, 2, 3, 4, 5. So counting is equal to an empty list. And then I would need to, would I do a for loop in here? Like for element in element in range here. Okay, like that, maybe. And now I do element, element, element. Okay. So I am going to, there's no way to see if we can do so I want to stop recursing here, and I don't even want to do anything else. Maybe I could do a flag like return, I don't know, -1, and then result is equal to here if result is not equal to -1, then we just return self.p. Okay. Backtrack on 0 and return backtrack on 0. Ooh. Okay. Is this correct? I don't think it's gonna be num. So I don't think it's num, and I don't think, like, why does this matter here? Do I have any more water left? No, not really. So this for loop is going to give me the 0, 1, 2, 3, all of these elements, right? And I need to figure out, like, once I've reached this last element, okay, once I've reached this last element, then I'm going to check if it's valid. If it is valid, I return this, okay? And that's where the flag comes in. I think that part is correct. Iterates through. What I'm less confident about is if it doesn't select a 0, well, it has to select a 0 in the first place. That's one, and my algorithm doesn't account for that, so that's not a good. Maybe I have to do like start. Okay. So I have to put start here. Oh, which actually that would have caused error anyways if I didn't. Okay, so and now the other guard that I want to put in is if not right, if n is 0, then 2 to the 0 is still 1, so I think we would have that 0 right there. Actually, so that kind of guarantees that we have something. Okay, whatever. Okay, so we solved that, but let's just say like okay, so I put that there. But if we don't select this one, does it come back to it? And we're going to put two elements in there at the same time. I don't even think that this is going to run. I think it's going to, yeah, okay. Yeah. Okay. How would you solve it? Okay. How would you solve it? Okay. Gray code basics. A gray code sequence of length to the n is a list of numbers where each adjacent pair differs exactly by 1 bit. It's a well-known sequence used in error correction and digital systems. Generate standard gray code. You can generate general standard gray code sequencing using this formula. Okay, great. I think that's bitwise shifted over by 2, or by 1, I mean. Normally it just looks like I shifted over by 1, but this one looks a little bit like hold on, squished together more. And this is what, exclusive or something? Anyways, ensure circularity. Because gray code is naturally circular, first and last elements. Well, oh, okay, yeah, I didn't even put that in there. Had a visited to the previous. Okay, this is what I did. I have this. I have this, okay. If I, okay, so I did this. If I not in visited, and this. So is that all I needed to change? Was I need a set? I need this like visited set. Visited and this. Then we do this. And then this one, it said num. I'm not sure why num. +1. Okay. which means that we actually did hit the base case, which we returned this. So maybe it worked. Well, okay, no, it didn't. Awesome. Dot pop. Oh, obviously. We need to do visited dot add element and then visited dot pop element. Okay. I still don't understand why that is num right there. Add start. Oh. Okay. What else? Oh, right, set is going to be, so we don't remove element, and then this one is going to be p dot, I think we can do remove as well here, right? No. Okay. We're just gonna copy and paste this and see where it. So yeah, I think he is getting rid of this and then doing if what self dot p at the last index is equal to last num, and now this p at the last index, right? Then we return that p, yeah. And then we don't need num plus 1 anymore. Okay. And I don't need this. I'm not sure. Okay. So apparently we were trying to return -1. But we should always end up hitting that. This one, or this one. So all right, so copy and paste it again. Right now, I'm just purposefully trying to just manually do everything to try to find all of the points that I completely messed up, and then we need to analyze this. Termination condition, self dot -1 equals last number. If no valid path is found, backtrack currently returns nothing. You should add return none. Okay. So let's forget this. I guess first let me try to look at the code and see if I can understand it. And then do an analysis of this. Okay, so total is equal to 1 shifted over by n, so that creates the n, or 2 to the n. Okay, that makes sense, because we're just taking that bit and moving it over. We create the start, okay, and we do visited. Cool, okay. We have this, and we have the backtracking. Okay. So if the length of P is equal to total, okay, so if we have total number of elements in P, and why can we do that? Because P is going to be from 0 to n, okay, or 2 to the n. Okay. If they are different by 1, and what is different by 1, self dot, so the last element and the first element, if they're, then we return P, okay, otherwise we return none. And then the for loop, element in range total, okay, that is kind of what I was doing here, or at least trying to do, right? Because total is the last element, and I just did last num, okay. If element not invisited, I understand that. I didn't do it correctly initially, so I need to go over like, okay, well, why did I not think of a set? Why did that idea not come in my head? It should have come in my head. I need to analyze why. But now that I see it, right? Now after I saw it up here, whatever, it makes sense. Okay, yeah. That was one of the questions that I was having. Remember when I said, well, nothing stops me from adding this element twice. Well, I should have immediately thought a set can solve that problem, because a set will have the number either in it or not in it. And I can determine which numbers are in the set in O of 1 time. Okay. And it's a valid thing. Then we can add the element, okay, to visited. So we're exploring placing the number in that slot. So then we append the element to P, okay, and then we backtrack. And that means that we're going to come back up to here, we're going to go back into here, and we're going to do another one of these starting at 0. And then if we already added it in the set, oh, okay, I'm starting to see how this works. Okay, if we've already added it to the set, then it's not going to do it again. And that kind of solves that problem that I was having of the two separate sides of things, right? Like this side, let's say I add something in the middle, like the 0, 1, 2. Let's say I add this. Zero, 1, 2, 3, 4, 5, 6, 7, 8, something like this, okay? And then let's say I want to add a 3 to the next element, but I don't have a 1 or 2. That's why when I go back up to do a backtracking, it starts back up at 0. Starts back up at 0, okay? And then I check, is this already in visited? If not, then it's valid. But I'm not going to add this 3. Okay, that kind of makes sense. Okay. Then we explore it, and then if we found something valid, we just return that result and just keep exiting out. Okay. Otherwise, we remove that element and go to the next element. So then we tried 0, that didn't work out. We try 1 and then see if that works out. Okay. Now, otherwise we return none. Is that part of the problem statement? Like, okay. All right, so doing some observations, I should have come into the situation where I knew that it was a set, or that a set would help solve the problem of I'm thinking right now of how do I determine if I've already added X to my answer? Whenever I ask that question, I should immediately say a set can help. Okay, next time I'm going to remember that. Next time I have that question, I want my mind to go to sets. Okay. The next thing that I can do is I need to continue to think through. I feel like I kind of took a glimpse into how this for loop actually benefits me within the backtracking and recursion framework. And previously, I had been a little bit confused about how it worked with those string questions. But in this problem, for some reason, it kind of clicked in my brain. I did a terrible job of actually like explaining it up here, but I feel like I kind of like see a fuzzy outline now of like, okay, I think I understand what's kind of going on. Like I feel like I fuzzily see it. But I need to think through it more. I need to continue to practice with it, and I need to try to get it more internalized and really strongly feel it. Okay? So, what I'm going to do, first off, I'm going to submit. Okay. I will not submit this. It was just running, right? Oh, okay. Apparently, do I not have internet, or I don't know. Well, I think I have internet. No, I don't. Okay, never mind. I don't have internet. Did you come back up? No. Okay. So, that's cool. So I was gonna save it, but what I will do is I'm gonna come back to this problem tomorrow, and I'm going to try to solve it again. And hopefully I have a better framework now that I can do it for a second time, and the second time that I do it, I will be able to more, because I want to get the feeling, right? That's really what my goal is to get that feeling of like, oh, I understand this problem. So I'm gonna do it tomorrow. Yes. I feel like there was one other thing that I wanted to say. Oh, right. So this for loop little trick was actually done in some of the other problems that I did like a week ago or whatever. So here's another one. And look, we have a for loop. Okay. And this for loop, so we do the backtracking and then we do the range. So I need to try to understand the meta connection between these two problems. Both of these problems use backtracking. Okay? And they are different problems, so they are trying to solve slightly different things, but there is a connection between them. What is the connection and what does that for loop solve in both of these that both of them had a for loop? Okay, so let's look at this. What were we trying to do? Maximum number of unique substrings. So we're trying to split it maximally, and this gives me the index from the string. So whatever index I'm at. So it says I try to split it here, I try to split it here, I try to split it there, right? So this is kind of like which element in this option set I'm given, okay? And likewise, what did I do in here? This is my option set. So this is the element that I'm selecting. And so that this is iterating through my option set. So both of these iterate through an option set. That's what the for loop does. And then I can choose that option or not choose that option in the string or in the list or whatever option set I have. Okay, so I'm going to be aware of that going forward, trying to make more connections to more backtracking problems. Okay, so next steps are continue to look at this problem and then come back tomorrow and try to hopefully do it quicker, but also understand what's going on more. So I'll be able to talk through it a little bit better. So today was a pretty good introduction to this problem, and I feel like, okay, well, we obviously need to continue to go over it and over it until we get it, right? But there's going to be a lot of good information and learning that we can do in this problem right here. So there we go. It was a good initial try at this problem. Anyways, thank you guys for watching this video. If you enjoyed it, subscribe, obviously. We are going to be making another video on it tomorrow. I hope everyone has a wonderful rest of the day. My name is Timothy Lee Grant, and I already just said have a good day. But anyways, goodbye.